So now the next topic we're going to talk about is kind of a combination of the pH effect and the complex ion effect. And we can kind of segment it into two different areas. So our last topic that we want to look at is called amphoterism. And this is kind of a special case, and this is what we can say about this. So amphoterism is a special case where a slightly soluble salt has its solubility increased due to pH effects in acidic solution and has its solubility increased due to complex ion formation in basic solution. So we're going to see an increase in solubility in acidic solution, and we're going to see an increase in solubility in basic solution. If you remember the term amphiprotic from the acid-base chapter, that means a particular species is going to act as both an acid or a base depending on the situation. If something is amphoteric, that means it's going to dissolve in both acidic solution and basic solution. So if we look at the effects of the solubility, remember we gave you a little graph that looks something like this, where if we plot solubility on the y-axis and the pH on the x-axis, for a non-amphoteric salt, we generally see the pH decrease, or as we increase the pH, the solubility is going to decrease. And the reason we have such a large solubility up here is because of the pH effect. We talked about this for a salt like magnesium hydroxide and how it dissolves very, very well in acidic solution. But if we have an amphoteric salt, we see something that looks a little bit different. We have here our solubility on the y-axis and the pH on the x-axis, and just like the non-amphoteric salt, the solubility is going to drop, but we also see a spike back up that looks like this. So what this tells us is we still have our pH effect here, and that's why the solubility is so dramatically high in one case. But the reason here is we have a complex ion form, and just like we saw in the previous example with the zinc, the complex ion formation is going to make the solubility increase in basic solution. You see this term in your lab manual when you take the group 3 and we're doing a separation. And one of the objectives here is to separate the nickel and to separate the aluminum. Nickel is not amphoteric, but aluminum is. So we can utilize this, and in terms of this curve right here, if we want aluminum hydroxide to stay as a solid, where in this curve do we want to be? If we want it to be a solid, we want the solubility to be very, very low. So we would want to be in this part of the curve right here. So in our group 3 analysis, we want the AlOH3 to be right in this particular pH range. If the pH goes dramatically lower or higher, that aluminum hydroxide will dissolve. as a chemist, what type of solution do we need to keep that pH into that region? We need a buffer solution. So you notice on your flow chart, to keep aluminum hydroxide as a solid, or to keep the solid present, we need a buffer. And on your flow chart, if you look at that, we do use a buffer solution. The reason we use that buffer solution is to make sure that our aluminum hydroxide stays as a solid. Because if the pH becomes too basic, we're going to be up here in this region, and we're going to observe a complex ion formation, and that aluminum is going to dissolve. So keep that in the back of your mind when you're going through your qualitative analysis procedure, that we need to make sure we prepare a proper buffer solution, because if we don't, the aluminum hydroxide dissolves and we won't be able to confirm that. Okay?